a piecewise function ultimately can kind of be exemplified really well through these couple of pictures right here, where it's really just a graph that's in different pieces that can be disjointed from one another, or if they want to connect, that's totally fine. Notice that if it's going to be called a piecewise function, that's different than if it was just like a piecewise relation, because if it was just a relation, then you're just any connection between inputs and outputs. But if it's specifically a relation that's called a function, then we know that by the definition of a function, each input maps to exactly one output, and that is occurring with these sorts of piecewise graphs. They are functions, piecewise functions, and you can see that because they do pass the vertical line test, and we can acknowledge that even like right here, it does pass the vertical line test, because when it crosses through right there, it's actually not hitting anything on the graph because it's an empty circle, so there's actually no point right there. So really it does pass the vertical line test, it's only hitting that point that you see right there. And then just right here you can see a couple graphs. The first one kind of looks a lot like the post office example that we saw. We call these sorts of ones step functions. They're a specific type of piecewise functions where you just kind of have flat little horizontal segments, that sort of thing. Even these are called step functions, even though it doesn't really look like steps or stairs, but it still kind of has horizontal pieces, and so we'll usually call those step functions as well. So one really big thing about piecewise functions is the fact that we're restricting the domain. And really what that means is that we are limiting the inputs of our function to a certain set. So it may not be necessarily all real numbers that are going to get mapped somewhere. It's only going to be a specific set. So let's take a look at some examples of how this kind of can play out. So the first thing right here says that we're going to restrict the domain, or limit our input set, for the function y equals 1/3 x plus 4, but we're going to limit that domain to only be x being equal to or greater than 3. So I'm just going to graph this first of all just normal. So it's just a line, y-intercept at 4, and then it's got a slope of 1/3, just like you see here. And so this right here would be the graph of y equals 1/3 x plus 4, but the domain of this graph is actually all real numbers, because every single x value does have a corresponding y value that it's going to get it mapped to. So for example, like this 9x value is a member of the domain, and it's mapping to a y value of 7 in the range, or like this 3 is mapping to a, that negative 3 in the domain is mapping to a positive 3 in the range. So now what we want to do, let me erase some stuff here, is we want to restrict the domain of this function to being x equal to or greater than 3, which means that from 3 equal to 3 and greater, these are the only x values that we want to be in the domain. So it just turns out then that really all we want to have graphed then is just the line that goes from that point and onward, so just like that. And so it's also really important that if our graph kind of got cut off right there, that we recognize that because x can equal 3, then 3 is a member of the domain. And so we can signify that by making sure that we have a filled in dot as sort of an endpoint right there to acknowledge that fact. So that right there would give us the graph of y equals 1/3 x plus 4, but only when x is a number equal to or greater than 3. So just in a similar sort of regard, if we just take a different equation, the equation y equals negative 2x, so I'll graph that like normal. It's going to have a y-intercept at 0, but it's got a negative slope, so it's going to descend downward, just like you see here. But now we're going to restrict the domain of this so that x is a number less than 3, which means that from positive 3 and then below, that's the only place that we're going to restrict the domain to. So that means the graph of this equation, it will go kind of forever towards the left and upwards that way. But the furthest it's going to go is it's going to go right there. And I'm going to put an open circle at the endpoint right there, because 3 is not a member of the domain in terms of how we restricted it right here. So with those now kind of separate, we actually really just put those sorts of things together when we're dealing with a piecewise function. So with this very first example right here, it says to graph the piecewise function. And to graph this piecewise function, you're going to recognize the fact that y is going to equal negative 2x, and then also that y is going to equal 1/3 x plus 4, the same things that we have graphed here just recently, and also with the same domain restrictions. So with the first one right here, we're really just going to graph f of x equals negative 2x, but when x is less than 3. So with x being less than 3 just means that part of the domain, and so let's just graph f of x equals negative 2x, and this is literally what we just did, of course, right? So y-intercept at 0, and then it's got a negative slope of 2, just like that, and then right there is going to be the first it goes, so an open circle going like that, and then we've got the arrow. So we're good with that piece, and then the second piece of this is to graph f of x is going to equal 1/3 x plus 4, but only when x is equal to or greater than 3. So when we're equal to 3 or greater is that part of the domain we're restricting this to, and then y equals 1/3 x plus 4. So start at 4 for the y-intercept, positive slope of 1/3, just like this, and then really it's just going to go like that with a filled in circle right there. We can erase some of this scratch work, and then there we have the completed graph of f, that piecewise function that we had defined there.